Okay, so we started dealing with the Dirac equation, and I'll sum up where we're standing. And to be concrete, I think towards the end of the lecture I made a statement about psi, alpha, and beta which wasn't correct, so I'll repeat it. Psi alpha and beta are 4 by 4. I think I wrote 2 by 2. We'll compose them in the end out of 2 by 2 matrices, but at the moment they are still 4 by 4 matrices. And they fulfill anti-commutation relation. And I is an identity matrix, just diagonals 1, all the rest of 0. Why do they have to fulfill it? We showed at the end of the previous lectures that if they fulfill it, we get the equation which means that each one of the components of the vector psi, psi1, psi2, psi3, psi4 fulfills the Klein-Gordon equation. We showed that at the end of the previous lecture. Okay. And now basically, this is where we ended last lecture, and now I'll bore you to death with notations for the simple reason that there's a lot of notations in this game, and after we'll do some notations, first of all, you'll perhaps understand all kinds of things you see in literature. And the second, it will put us in a place where we can go and solve this equation and try to understand what actually does it tell us. This equation, which looks very innocent at the moment, has a lot of deep physics in it. Okay. First notation, instead of using beta and alpha, one is the four matrices are written in a different way with gamma 0 and gamma I. I is equal 1, 2, and 3. Okay, just notation. Just to see what commutation relations, we know the commutation relations or anti-commutation relations of alpha and beta. Let's see what are the commutation relations of gamma, the different gammas. And it will be also a nice exercise in matrix operations. Okay, so what is gamma mu and gamma mu? Anti-commutation relation. Okay, first of all, it's just a definition. Let's just write down the definition. Okay, nothing to look at. We've seen it already. Some of you that did relativity or certainly general relativity ran into this matrix G mu nu. Let's check it. It's not a given, it's just the result. Okay. Let's look on the case gamma equals 0 and mu equals 0. So basically what is written here is
question.
Yeah.
Gamma F is equal to beta. Please subscribe.
Beta was the oh, sorry about this, but beta, alpha has three components. You see, you have a dot. Beta is just a 4x4 matrix.
Okay. So gamma 0 is the mid, matrizen בפני עצמה. Gamma 0. So. Okay.
Just a moment, I want to correct your something. Okay.
Each alpha
I have alpha 1, 2, and 3.
שכל אחד מהם זה מטריצה 4.
All of them are 4x4 matrices. We have here 4 matrices. And, well, basically writing it in this notation makes it completely clear. You have gamma 0, 1, 2, 3, 4. Sorry, no, 4, 1, 2, 3, and that's that. Okay, you can get a feeling that it's somehow connected to one time-like and three space-like, where the space-like of the alpha is very clear, the time-like of beta we'll see in a moment. Okay, but you also see here, this is plus, all the others are minus, time-like and space-like. Okay, so the first one is very easy to check, okay? Because gamma, if both of them are 0, so we have gamma 0 squared. Gamma 0 squared is beta squared. Beta squared.
Wouldn't that be a matrix with 2 on the diagonal?
Mm-hmm. Yeah.
זה משוואה שמתאימה רק לפרמיונים בעצם?
Welcome. Dirac equation is an equation only for electrons. When we are going to add something else, like photons, and you want interactions between photons and electrons, if you want also to quantize the photons, you're at a dead end. You go to field theory, you get QED, and you have there all kinds of divergences. Now, one of the great contributors to this QED formulation was Feynman. There's a well-known anecdote that Feynman sat at some lunch near Dirac, and Dirac was a person who generally spoke very little, and Feynman is known as someone who liked to speak a lot. I mean, the whole lunch he tried to engage him in conversation, and in the end of the lunch, Dirac told him, "So, are you working now on your own equation for QED?" And that's, I think, is the only time someone really silenced Feynman. Because here, this is a closed, nice equations, not too much mathematical problems. QED is riddled with mathematical problems. That's the last equation that they were able to write that is well-behaved mathematically. No divergences, some little problems that we'll address, but still. So, what do we have? Schrödinger, that's the motivation for that. Electrons, non-relativistic. Dirac, electrons, relativistic, and I hope that by the end of this lecture you'll see that Schrödinger's equation is the small velocity limit of this equation. Once you add interaction with any other particle, especially bosons that don't conserve number, you have to go to field theory. We wrote field theory for photons. And Klein-Gordon, not Dirac. Coupling Dirac equation with the field theory will give you QED. And basically, once you'll know the notations, you would be able to open any textbook see the Lagrangian of QED and understand at least what's written there. Okay. One time-like and the other one is space-like. Okay, we'll go to mu is equal 0, so it's beta. Nu is not equal 0, so it's beta times the appropriate I. Vice versa. Beta times beta is 1. So you have your alpha I beta. You can use this anti-commutation relation. Okay. Both of them are space-like. Okay, I just wrote it down. Again, I'm using the commutation relation. The reason is once I get to the two betas, one after the other, it's 1. Okay, the anti-commutation just gives me minus and beta square. And here I have this anti-commutation relation. So it's delta ij minus. Okay, so that's the reason we got this commutation relation. And this, I think, is a notation invented by Feynman to shorten the notation. It's elegant, but at the end of the day, for a novice, you have to always translate back to understand what's written. So I'm rewriting Dirac equation.
equals 0. It's the
Do you see why? Okay. That's something that always happens when one doesn't really, when one looks at a complicated notation but doesn't translate it directly. What's written here really? Minus I alpha 1 dou 1 x minus I alpha 2 dou 2 minus I alpha 3 dou 3. And if you want, here it's okay. Multiply it by beta. So here you'll have beta square, which is 1. And all the others will have either beta or beta times alpha 1, beta times alpha 2, beta times alpha 3. Exactly. That's Feynman notation, do bar. So there is only H bar. Which is basically it's not square n to the power 3, it's 1, 2, 3. Gamma 1, gamma 2, gamma 3. Okay, again, it's only notations, but you have to admit this is much more impressive. Okay, so I need matrices that will follow these anti-commutation relations. Okay, so we broke the 4 by 4 matrix to 2 by 2 matrices, and First, you should convince yourself that it actually follows the commutation relations that we have written.
What is written in alpha I?
The same, just
Without the
remember that gamma I is beta times alpha I, and the only difference is this
The minus
minus on the lower block.
Okay.
Okay, so usually when one goes to solve Dirac equation, one doesn't start with this very general formulation. One goes and writes down explicit this form. So let's do it and see how one can get a solution out of it. It's a vector with 4 components, and I'm breaking it up to 2 vectors with 2 components. And it's known as spinor, although at the moment it's not clear why are we using this name, except that you are used that a spinor is something with 2 components. Okay, so I go back to the equations that I've written up and substitute the gammas with the definition and write, and I get 2 coupled equations. And just so we'll be all on the same page, this means sigma 1 dou 1 plus sigma 2 . Yeah.
בשורה הראשונה זה צריך להיות
Thanks.
Probably with a minus sign.
No, here should be a minus sign.
and it's delta phi, not delta.
Great. So we have two equations. Well, that basically comes out from the block structure written here. But they're coupled. In phi, we have components from chi, and from chi, we have components from phi. Okay. So, first of all, first question is, what are the conserved quantities in Dirac? We said, without really proving, that Klein-Gordon has a problem of conserved quantities. Let's say that the Dirac equation has conserved quantities. So I won't go into it in a general way. I'll just illustrate how we are thinking about it and proves the result. Okay, what is the usual conserved property in Schrödinger's equation?
Energy.
Before energy, the basic conserved quantity.
Charge.
Charge doesn't really appear even in
Mass.
Integral over psi square is equal to 1. The simplest thing is that you have a particle, it's there. Now we have here 4 components. So how do we express it? Well, if we have a vector, if we have a scalar, we took a number, psi, and multiplied it by psi complex conjugate. If we have a vector, we'll multiply it by the adjacent complex conjugate or by the dagger. So basically, let's look what happens to the quantity psi dagger psi and shows that it's conserved. If you remember, how did we prove that psi times psi complex conjugate is conserved in Schrödinger equation? We took Schrödinger equation, performed on its complex conjugate, multiplied them, and showed that it's conserved. Same idea here. So I'm writing now the equation on psi dagger. So I'm taking the equation written up and perform adjacent on it and complex conjugate. So psi moves from here to here as usual. The derivative is backwards. So another piece of notation. I told you that today you'll be fed with a lot of notations. All this tells me is that the arrow is on the other side, so I perform the derivative on this, not on what occurs ahead. Gamma becomes gamma dagger. Very clear. I know to write gamma, so I know to write gamma dagger. And then there's a scalar, so nothing happens to it. And it doesn't matter if you multiply psi dagger by m or m by psi dagger.
There is a minus.
And
זה
it's
reflects
still a minus. No, no, it's a plus because this
Because
had a
I-
minus. Good. So let's see what happens to our matrices once we perform on them Hermitian conjugate. Okay, beta simple. Here I have to be a bit more careful. I have a multiplication of two matrices. So it's alpha. Checks that alpha I dagger is the same as alpha I.
But אלפא I יש פאולי מטריס שזה imaginary.
Check
So what?
לא, זה
זה מי כן? מוסאי ומוסאי.
לא, זה סיפור.
אז נכון, סתם.
Okay, so it's a bit more cumbersome. But it's okay. Definition. Yeah. And
It's not it's an equality because
I'm just replacing
here it's just the dot. Psi bar down.
That's a
Yeah, down. The last equation.
okay. I recommend to do the two steps in between, but okay. basically I have two equations here.
Richard, can you explain again the last line with the psi bar? The
Okay.
yeah, it's a definition, but how did you get the last equation?
Basically, my problem is that I'm stuck with a beta there, right?
Okay.
So I had something that actually it would be easier to good that you pointed it out. Didn't write, of course. These things. And now, where did we write the definition of alpha? Beta dagger is just gamma 0. And just don't take a minute after the lecture and just write it down. Perhaps, where did I? You had the definitions. Just use the definitions and said, yeah.
But then the beta dagger multiplied by beta should give us the unit matrix. And then the gamma f at the end should be
Okay, let's do it like this. I just don't want to mess it up and spend time on it. Finish it up and check what comes. This is definitely correct. Okay? Alpha I dagger, yeah. The reason it's hidden here and I don't want to do a mistake in copying it. Okay, so the important thing is we got to this point. We multiply this by psi bar, we multiply this by psi to the left and to the right, and we just add them. So what do we get? M falls off, hence is that. Can't forget about the eyes. Put put in the definition. So I just
ריצ'רד, במשוואה לדגל צריך להיות סלאש על המיוט?
here.
No, the last one. כן, בכללי גם שם.
No,
No.
every time the slash just
הוסיפה גמא.
incorporates a
Okay, I
gamma.
didn't see the gamma.
So over there, you should.
אז צריך
Here
את
I've messed it, if that was a question. And of course here, so instead of using this esoteric notation, I'll just write down what it means. Yeah, just all I did is just wrote the derivative to the left in a more conventional notation. Since gamma doesn't depend on x, y, t or z, t, x, y or z, right? So all I do is this derivative, this is not in the game, and this derivative, which is exactly what's written here. Yeah.
What came first, the Dirac equation or the Pauli matrices?
Pauli matrices.
So מה הם הגדירו? מה הם הגדירו המטריצות האלה?
In a moment, the spinners,
אבל הספינורס מגיעים רק ממשוואת דיראק.
it's like asking me, what is the energies that Bohr wrote down? They have a meaning only after solving the Schrodinger's equation of the hydrogen or whatever atom, right? So Pauli already in 22, 23, building on work that was done by Goudschmidt and what's the name of the but another Dutch guy who came up with the idea that the spectrum in a magnetic field could be explained if the electron has an additional degree of freedom that they called spin for very bad reasons. But and Pauli played a lot with it in 24 and 25 to explain the spectrum of the atom in a magnetic field, and used these matrices. He understood that you have here a doubling of, well, they didn't even call it then wave function, some quantum number. And he had these matrices and did with it operations, but in the same way that that Bohr had energies and could tell you connection with with the quantum number n or L or P, or without seeing from what equation it comes out. So the answer is Pauli equations existed a few years before Dirac gave an explanation. And well, I'm waiting with the statements to show you a solution, but basically both spin and basically anti-electrons or antimaterial comes out from this equation. But at the moment, we're still slogging on here to try to write some, to understand the equation and write some solution. Okay, so at this point in life, you could immediately tell me something interesting about this property.
It's constant.
It's constant, and these are actually the natural.
Okay.
So I have here both conservation of charge, if you want, and conservation of current. So just to be more concrete, just write it down once. So the time part, J0. Which is the density. So basically our intuition was correct. Gamma 0 square is just I. So if I multiply this 4 vectors psi with its Hermitian conjugate, I get a quantity that's equivalent to the density. Here I wrote it down separated to its 2 spinors. And if you want to write down J, finally, we are ready to do something with this Dirac equation. And what we'll do is free particle. What is the solution for the wave function of a free particle in Schrödinger equation?
With IKX.
Exactly. E to the power I k vectors multiplied by r vector. Let's see what we are getting from the Dirac equation.
אפשר עוד טיפה?
נוכל לעלות את זה. זה השורה האחרונה שלנו.
So we have this two-component equation, but let's start even writing it down as a 4-component and then see what happens. And here I have inserted H and C squares that we threw out at the beginning. Why? Because I want to compare the results to the Schrödinger equation.
H, it is the Hamiltonian, which will resolve the equation.
Dirac equation is like a Hamiltonian, right? Just to remind you, so basically here we'll have to get the solution for 4 components of the wave vector, 4 functions. Okay. Since if none of these guys depend on T, and none of these guys depend on T, then I can use the same trick that I used for the Schrödinger equation to separate stationary from non-stationary solutions. And then I get which is equivalent to the Schrödinger equation, 4 components. So here, and the structure is more complicated. Or basically, I guess, if you want, that the spatial part, psi r, will be some function of r that I have to find, times e to the power I p dot r. And UP is still a 4 vector. The vector is 4 components. All I did is use it here and perform the derivative.
Can you explain again where psi p came from?
Okay, I'm here, right? So I assume psi r, which is I assume that I can write it in the following form. This is a vector with 4 components. Same as in the previous case, it has a phi component and a chi component. Only thing, if I perform the derivative, instead of a derivative here, I have p. P comes down. That's
yeah. This is the equation that's independent of time, right? Because there is
I said the set.
to separate the time and the space.
Exactly the same thing that I did for Schrödinger. Not I did. That was done for Schrödinger equation. Why? Because nothing here depends on time. If you want to come with a theory that C depends on time, then you have to have something else. Okay, so now I go and write down the equation explicitly.
כן, שיקלי לעצמי.
Okay. Two by two blocks. Remember, sigma is a 2 by 2 equation, and here just usually people don't bother to write I to diagonal matrix. This one. If it disturbs you, you can put it. But it's two. All this vector is a 4-component vector. Okay. Again, E here is if you want to be that times 9. Okay. Let's just subtract the right end of this equation. Basically, I subtracted this part from this part, but I got the minuses right. Minus. Okay. Okay. I just wrote the two blocks separately. this guy times this guy and this guy times this guy. Let's assume. Let's put it in and see what we get. Just wherever high P appeared here, I substituted it by this, and we'll see in a moment what does it mean. And just multiplied the result. Now, yeah,
Can I ask a question?
sure.
Something doesn't feel right. I don't know if I just don't understand it or. The sigma matrix is a 2 by 2 matrix, right?
Right.
And then the p vector should be a 3-component vector because it's multiplied by
Remember, sigma vector is sigma 1 plus sigma 2. Sigma 1, the first component, sigma 2 is the second.
Oh.
Unfortunately, I have deleted it already, but
Okay.
I'm
Something just didn't.
I'm trying all the time to emphasize it.
Thank you.
It's sigma 1 plus sigma 2 P2 plus sigma 3 P3. XYZ.
Okay.
It's confusing because sigma vector is
Not really.
no,
No, it's a vector of matrix.
of matrices,
Yes,
and
okay.
from the beginning I think I've already emphasized
yes,
it
you did.
twice.
You did, but I.
No,
Way too tired.
it's hard. It's It's, as I said, it's a new notation, and new notations are always hard to comprehend. It takes time till you get used to them.
Thank you.
Okay, this is just try it and convince yourselves.
Try and never.
Because I want to get to the main result here. And the first result will look familiar. Okay, this is just what comes out if you believe this piece of math. So what does it basically tell you? You have solutions for okay, one branch of the solutions we understand immediately. This is the relativistic form of a particle with momentum p and rest mass m. The LRZ solutions, I left a question mark, come to it in a moment. And
It's larger than or equal to, right?
yes. So what did I do here? I chose this solution. Okay, because here basically any constant solution will fulfill the equation. And go back here and write down all 4 components. And what did I get? Let's assume that we are moving at relatively small velocities.
שתי אפשרויות של VP, כן, קורספונד לאפשרויות של האנרגיה. למה מחר?
Anything I put here fulfills this equation, right? As long as this is a value of E, right? Any combination. It's a vector of 2 components, any constant vector fulfills it, right? So I'm looking on 2 bases of it, 1, 0 and 0, 1, and just look what is the full solution. Okay, and what does it tell me? That as long as the velocity is small compared to the rest mass, basically I have this solution or this solution. All these are negligible, and it's times, where did I write it? Up there, EIP dot R, which is the Schrödinger solution just multiplied by the spin, or things that you already did ad hoc with no good reason. But it's a result of the Dirac equation as long as P is small compared to the rest. Now the same game so I can go back and write
So for big masses also. For big masses it will also be you don't have to be P is much smaller than MC squared.
I'm looking on this.
Yeah, but אם המסה מאוד גדולה, אז זה גם כן, לא רק במהירויות גדולות.
So as long as this, but remember P is also V times M in the non-relativistic. So you have here M on both sides.
ב-E יש לי עוד M.
So either this are the solutions
For low energy.
for low P limit. So this one, you know, this, who cares? It's an additional phase, but anything that you calculate with it just is cancelled out. So That's a justification why you go to Schrödinger equation, and all that you have to add is these spins. So that's the origin of spin. Now I could return to this game and do the same game and go through the whole math.
אבל זה לא כאילו שהמכנה והמונה מתחלפים, כאילו שהאיברים לא
One difference that it's a minus instead of plus and a minus here.
אוקיי, המשוואה הראשונה.
Why no need for a minus?
Hmm?
No need for a minus in the numerator.
Did I miss or something? Oh, no minus. Right. Okay. And this guy I can write instead. Colors that I don't need to write it all again. And this is for the negative branch of the energies. So basically this follows this. Okay, we go, so we get here basically either 0, 0, 1, 0 or 0, 0, 0, 1, perhaps an additional plus or minus. What is the meaning of this thing? So basically, Schrödinger equation, we had an electron represented by an eigenvector that had just one scalar component. Here we have an electron which has 4 components. Now, the simple understanding. 2 of those components, the phi and the chi, stand for either spin up or spin down or any combination of them. But that forces you to have spin, or at least an additional quantum number that represents the probability of being either in this state or in that state. Because of the way that it couples there with H and C, it is actually a magnetic moment. It has the same units, it behaves like a magnetic moment. Okay, lovely. So we understand phi having 1, 0, but what is the chi? The chi corresponds to the negative states. Then we're going back to the old problems that we discussed in the beginning of this relativistic part, in the beginning of the last lecture. What are those negative states? They're terrible. You can create more and more energy by going to a lower and lower state. Here comes the great invention of Dirac, which actually took him much more time than writing down these equations. He had these equations, and in the beginning he was convinced that this is the electron, and the other solutions, the phi, are the protons. But there's one small problem. M is the same in both of them, and doesn't work. Electrons don't have the same mass. Then he had the insight of basically coming and saying, look, both solutions exist. In the universe as we see it, all the negative states are already filled. And when something, so basically, okay, that's a spectrum. All these states are filled up. It's fermions. Filled up state can't acquire another electron in it. So what do we see in nature? We see only cases where for some reason an electron that fills the negative part jump to the positive part. This behaves like a good old electron. This creates a hole, and a hole behaves like an electron but with a positive charge. That's a positron. Now, this is mind-boggling because basically it tells us that the ground state of the universe is filled by an infinite number of electrons. But as long as they're filled and not in the game, we don't see them. They have no influence on us. Once they vacate a state here, we can't see it. That's a positron. And a lot of times in vacuum, we actually see, we supply energy like a photon, and you get a pair of electron-positron. And in this picture, it's very natural. So Dirac equation actually tells you, you want to write down a relativistic quantum mechanics, you're paying a price. You're paying a price that your basic fermion has to have spin half, which is two of the components that we've seen, and it has to have a partner, which has the opposite charge. Again, something that was confirmed experimentally. Yeah, so, just let me finish. So basically, going on a quest to fulfill relativity, and came back with two things that, one, spin was known to exist, had no explanation, and antiparticles, no one even suspected that they exist. So when you are asked what is the basic prediction of relativity, it's not time shortening or length elongation or whatever, spin and antiparticles. Okay, what?
So, בפונקציית גל שהיא וקטור של 4 פונקציות גל, יש לנו 4 ערים שונים?
לא, מה זאת אומרת? יש לך בפנים פונקציה 1, 2, 3, 4, אתה שואל, אתה יכול לשאול מה קורה לכל קומפוננט בכל R. אתה רוצה לבחור R'ים שונים, אז תיארת בדיוק כמו שיש לך שדה עם 4 קומפוננטות, ואתה בא, אני רוצה את הקומפוננטה הראשונה פה, את הקומפוננטה השנייה שם. או אני שואל E של X, שדה חשמלי בכיוון X פה, ו-E בכיוון Y שם. אתה יכול לשאול, בכלל.
אז כשאני מתאר את כל הפונקציית גל של הוקטור הזה, אז אני לא מתאר כלום. אני לא יודע שום דבר על מה קורה בתוך הקומפוננטות, זה מה שמשנה. קומפוננטה בפנים היא משנה. הפונקציית גל עצמה היא כלום, היא לא אומרת שום דבר. כאילו,
אני מפספס, וכשהוא סקלר, למה אותה שאלה לא קיימת?
כשזה פונקציית גל אחת, אז אני יודע, היא מתארת לי במקום הזה, יש לי סיכוי למצוא אלקטרון.
אז אני אבוא ואשאל את השאלה, במקום R אני רוצה אלקטרון עם ספין אפ, תחשב את הקומפוננטה העליונה. אתה רוצה אותו בספין דאון, תחשב את השנייה. אתה רוצה את הפוזיטרון עם אפ, תחשב את השלישי, תחשב את הרביעי.
אז יש לי עוד שאלה, כאילו, מה זה אומר, אם זה חור, פוזיטרון זה בעצם חור, אז מה זה אומר שיש לו ספין בחור?
היה שם אלקטרון. לאלקטרון הזה היה איזשהו ספין, הוצאת אותו משם, זה חור, אבל הוצאת אלקטרון עם ספין.
אז הוא חייב להיות הופכי
אז זה הופכי, לא רציתי אפילו להיכנס לפרט הזה. הופכי למטען והופכי
זאת אומרת, אם אני יודע את הספין של אחד, אני יודע את הספין של השני.
נכון.
אבל במיקום זה לא ככה.
אתה אומר לי שהם יכולים להיות שני פונקציות
במיקום הם יכולים להיות, האלקטרון יהיה פה והחור יהיה פה, אבל בספין...
אבל אפילו בצורה שכתבנו לזה, המיקום הוא פאזה סך הכל. זה חלקיק חופשי והוא קיים בכל מקום. כאילו הצד הבא זה לפתור את משוואת דיראק בשביל אטום המימן ולראות את התיקונים. לא ניכנס לזה, ראיתם את קפיצת המדרגה בשרדינגר בין משוואת שרדינגר של חלקיק חופשי לבין אטום המימן. פה זה עוד כמה מדרגות בדרך. נורא מעניין אותך, זה מופיע בטקסט, זה הפתרון. שוב, עם קירובים מהסוג. Okay, so I guess we'll stop here.
תודה רבה.